You can start.
Okay. Good afternoon, everybody. So as I understand, the Rees representation theorem is going on, right?
Yes, sir.
Yes, sir.
Okay. So the bad news is that phase is not yet over. We have to deal with Rees representation theorem. That's pretty fundamental to us. But I want to put things into perspective to understand what exactly we are trying to achieve. See, the point is, in analysis, the heart of the subject lies the notion of approximation. So far, the most naive notion of approximation is the notion of pointwise convergence of sequence of functions and things like that. However, measure theory gives you different notions of approximation by which you can approximate bad guys by good guys. Say something like you can approximate discontinuous functions by continuous functions or differentiable functions by non-differentiable functions. That happens. And the heart of that method of approximation on which analysis basically relies on lies the notion of regularity of a measure. And that is what I'm going to start with. You have actually seen the notion of regularity of a measure that appears in the statement of the Rees representation theorem itself. But to bring it into focus, I will state it precisely. What do we mean by regularity of a measure? And then we will compare this notion of regularity with the statement of the Rees representation theorem. That is the second point which you see in the slide, comparison with RRT. That what exactly Rees representation theorem gives us in terms of regularity. Then we will review the statements of the Rees representation theorem, which you already know, which has been done by Professor Srivastava. And then some of the remaining parts of the Rees representation theorem, which focuses on the notion of regularity, I will have to prove. Okay, so that is the plan of the first lecture. We'll try to go slowly. If it doesn't get over in the first lecture, there is no need to be panicked. We can go to the second lecture itself. We have enough time. So is that understood what I exactly said? Have you understood the plan? That we're going to start with a new notion, which you may not be familiar with. But even if you are familiar with, it's still better to review it. So we start with the notion of so-called regularity of a measure. Okay. So let me start. So the setup is, as usual, what we are dealing with. X is again a locally compact house dog topological space. Then the most natural sigma algebra on any topological space, what one can think of is the so-called Borel sigma algebra. Do all of you know the meaning of Borel sigma algebra?
Yes, sir.
It is the smallest sigma algebra containing all the open
All the
sets.
open sets.
Correct? Absolutely. Now, given a topological space, the most prominent sets which I can think of, I don't know any structure. I just know some abstract topological space is given to me. The only sets which I know to start with are open sets. So things have to be defined somehow in terms of open sets. Okay. So what is the definition? So it is the definition of regularity of a measure. Suppose mu is a Borel measure. What do I mean by that? It means mu is defined on a sigma algebra which contains all Borel sets. So it could be defined on the Borel sigma algebra, or it could be defined on a bigger sigma algebra. The only demand is that all the sets of the Borel sigma algebra should be in the sigma algebra of the measure. Then mu is called a Borel measure. Okay. Now, given a Borel measure, suppose E is a subset of X. Which is a Borel set, we say is outer regular if you can approximate the measure of the set E from outside by open sets. That is, mu of E is the infimum of mu of V, where E is subset of V and V is open. So the set E, a Borel set E, if it satisfies this property, then we say that E is outer regular. Now this should not be pretty unfamiliar to you if you have gone through some part of the proof of representation theorem. This already appears in the representation theorem. Do you remember where? So let me remind you, when you are starting the representation theorem, listen to me very carefully. You have been just given a positive linear functional and a topological space, nothing else. So what is your first attempt? What are the sets on which you may like to define measure of a set? What kind of sets? Well, it should obviously be the sets about which you know something. Those sets turn out to be the open sets because it's a topological space, so it has got open sets. So what representation theorem tries to do first is try to define what should be measured of an open set. And that is done using the positive linear functional and manipulation of compactly supported continuous functions. Then your next step is try to define measure of any set. Now, do you remember how we did that step? Take any set E. You already know measure of open sets makes sense. You try to define measure of an arbitrary set. How do you do that? Well, the prescription by representation theorem is you look at all open sets which contain E, look at their measures. It now makes sense. Look at their infimum. That is mu of E, right? Yes?
Yes. Yes.
This is what was done for an arbitrary set E, and that is precisely the notion of outer regularity. Okay, so this is the definition of outer regularity of a set. Now there is a notion called inner regularity. So again, E is subset of X. This is called inner regular. If measure of E is the supremum. That means you are, since it's inner regular, that means you are trying to somehow approximate by certain objects which are sitting inside E. What are those objects? Well, it's measure of K, where K is subset of E and K is compact. So a set E is called inner regular if its measure is supremum of the measures of the compact sets sitting inside it. Okay. And then comes the notion of regularity. A measure mu on X, mu is called regular if every Borel set E is inner regular as well as outer regular. So a regular measure basically means that it has a property that take any Borel set E, then you can approximate its measure from inside the set by compact sets which are sitting inside E. And you can also approximate the measure of the set from outside, from the bigger sets, open sets, which contains E. Then the measure is called the regular measure. And these are the best possible situations which we can have. Now, just one more thing I would like to say before I move on to the next topic, that is comparison with representation theorem, that one should remember that as such, the abstract subject measure theory deals with a set, a sigma algebra, and a measure. That perhaps you have seen in the first part of lectures of Professor Joydev Sarkar, right? But then what we are trying to do is that now you have an extra structure of topology of the set. And regularity is the precise notion where the topology and measure theory starts interacting with each other. Okay, such a thing doesn't happen outside topological spaces. Obviously, it cannot make sense. Okay, so regularity is basically, think of it as interaction between topology and measure theory. Okay, we now come back to the comparison of Rees representation theorem. That what we know from the statements. So I just write it as a note. All those things are given in a lecture notes, which I have already communicated and it has been posted. Now the measure mu coming out of Rees representation theorem it comes with certain properties, right? One property is it says that every Borel set is outer regular. This is because I have reminded you again that how measure of an arbitrary set was defined in Rees representation theorem. It was defined by this formula that mu of E, as long as E is any subset of X, is infimum of mu V. V subset of E, V open. This is how mu of E was defined. That means the notion of outer regularity is actually inbuilt in our definition in the construction of Rees representation theorem. Am I making sense?
Yes, sir.
Okay. Next step. And here there is a problem. If you remember the statement of the Rees representation theorem, forget about the proof, just a statement. In one statement of Rees representation theorem, it says that if E is open or measure of E is finite, then E is inner regular. In our language. Because the statement says that either if E is open or measure of E is finite, then measure of E is supremum, measure of K subset of E, K compact. This is in the statement of Rees representation theorem. Are you in agreement that this was one conclusion of Rees representation theorem?
Yes, sir.
Yes, sir.
Okay. Now this gives rise to a problem because if I have a Borel set which is not open, that can happen, right? Because maybe countable intersection of open sets, things like that, that will be in the Borel sigma algebra. And if the measure of that set is not finite, then Rees representation theorem is not giving me inner regularity. So Rees representation theorem gives me inner regularity only for two kinds of sets, if E is open or its measure is finite. But I am going to be more demanding. I will actually need inner regularity for all Borel sets. And that cannot be done with this Rees representation theorem unless you put some extra topological structure in the space apart from locally compact and Hausdorff. That is what we are going to do in the future. That means I will assume more topological property on the space to get inner regularity for the Borel sets. Is this clear what I said?
Yes, sir.
Yes, sir.
Okay. So this is the second part of my thing is over. This is the connection with Ries representation theorem. We just realized that there is an inherent problem in the Ries representation theorem if we are so demanding about regularity, actually inner regularity for every Borel set. That does not come from Ries representation theorem. So we have to do something else. Okay. Let me now quickly review what has been proved for Ries representation theorem, and then I advance our discussion with proofs of some more parts of Ries representation theorem. So our situation is, so coming back to RRT. So what is the situation? X is locally compact Hausdorff. A positive linear functional called big lambda from CCX to C is given. We have to construct a measured mu such that this lambda of F is given by integration with respect to that measured mu. The only property we know about lambda is that lambda is linear and it's positive. That is, F non-negative implies lambda F is non-negative. This much is given to us. Okay, then first step, we define measure of open sets because that is the building block of the topology. Those are the only sets which you can have. But fortunately, you are not asking a question. I don't know whether any of you have asked. That's a good question. That you have given me an abstract locally compact topological space. I have never seen in my life any such set except inside Euclidean spaces. Then what do you mean by a positive linear functionals? What kind of examples you have in mind? Have you asked this question? Or has it been discussed? If it has not been discussed, no problem. In the tutorial problem, we'll discuss some such problem because apart from the measures, this positive linear functional is also a problem. But how does one define a positive linear functional on arbitrary set X? But let's not discuss much about it. So let's quickly get on to the definition of measures of open sets. So V open, we have defined measure of V to be equals to supremum of big lambda F, where F is simply compactly supported continuous function whose support is contained inside V. It is written as F. Okay. So what is inbuilt in this is something like this lambda F, which is actually wrong. But for my understanding, I will like to think of this lambda F as measure of the support of it, the compact set. And then you are looking at its supremums. That means some amount of inner regularity is already inbuilt in the definition. I said some amount because it's not really the case that big lambda of F is measure of the support. But let's pretend that some such thing is actually happening. Okay, and then measure of any set that I call 2. So take any set E in X, then we know what is mu of E. It is defined as infimum. Mu of V V open. Sorry, this is the other way. V open. So outer regularity is actually true by construction. Okay. So this is how one should approach the proof of Ries representation theorem. The focus is actually regularity, and you are defining things in such a way that this is being inbuilt in the construction as much as possible. Okay, And then it has been proved that this mu is monotone. That has been proved. That means bigger sets have bigger measures. And second thing is it's countably subadditive. That also has been proved. So in the language of measure theory, this is somewhat one calls an outer measure. So an outer measure has been created, and then the only job which remains is typically outer measures are not countably additive. That is, if you have disjoint union of sets, then measure of the disjoint union of those sets nicely sum up to the measures of the sets. That is countable additivity, which doesn't usually happen. So what one needs to do is cut down on the number of sets. Don't try to define it on the whole power sets. Choose some good sets, hope that they form a sigma algebra, and your mu restricted on that subclass is countably additive. That is the whole idea of defining measures. So obviously this brings us to the definition of the sigma algebra, and that is what Rudin does next, and that has been described to you anyway. So towards sigma algebra, one defines something called MF. So it is all those E such that some good sets, it has two properties, that the measure of the set is finite, okay, and two, the property that inner regularity should happen. That is, mu of E. Inner regularity means approximation from inside by compact sets should happen. That means it should be supremum mu of K, K subset of E, K compact. K compact. This is how MF was defined. Okay. Now, what I can see is MF has been very cleverly defined in such a way that sets with finite measure, which satisfies the inner regularity property, has been carefully selected inside MF. Okay. Right now, I don't know whether anybody belongs to MF or not. And then one defines something called M, which we are going to see is actually a sigma algebra. I will not show it, but Rudin shows that M is going to be a sigma algebra, and MF actually will have a much simpler description. This M simply turns out to be all sets E in X, such that E intersection K belongs to MF. And this should happen for all K compact. Great. This is my M. This is how they define. So we are approaching abstractly, exactly the way Rudin does it. And then Professor Srivastava has put one important theorem, probably the first important step in Riz representation theorem, which cannot be undermined. That is, I do not know who belongs to MF, right? I don't know examples of elements in MF, but this result gives me something. That suppose K is compact, then this implies that K belongs to MF. Which is actually same as saying that if measure of K is, well, which is actually same as saying, let's erase this part at least, that measure of K is anyway finite, since K is in MF. Okay, and more importantly, that this measure of K is actually infimum. So far, I know that measure of K is infimum of measures of open sets which are bigger than K, right? Because outer regularity is inbuilt in the definition, which is here. Somehow I cannot get rid of this, this bar. What I mean is this. See, this is outer regularity, which is true for every set. So in particular, it is true for compact sets. So measure of K is actually infimum of measures of the open sets, which contains it. But this theorem proves that this is infimum of lambda F, such that is F is a compactly supported continuous function. Value of F lies between 0 and 1, and F is identically equals to 1 on K, right? This was proved. Are you in agreement? This was actually proved in the last class. And after that, Professor Srivastava tried to prove that mu is countably subadditive, right? So I'm going to take hints from here on, but one important information I got, that MF contains all compact sets. Incidentally, this also implies something more remarkable. So just note it here. So note. Suppose C is any closed set in X. This would then imply that C intersection K is compact. Correct? Closed subspace of a compact space is compact. But C intersection K is compact means by 4, my C intersection K is actually in MF. Because all compact sets are in MF. You now go back to the definition of M. M contains precisely those sets E such that E intersection K is in MF. But C intersection K is already in MF implies C belongs to M. So now I at least know that all closed sets are sitting inside M, right? If by any chance one can somehow show that M is a sigma algebra, then I immediately know that complements of these closed sets, which are open sets, are also inside M. And it would immediately follow that the Borel sigma algebra is sitting inside M. Okay, so one just has to somehow show that M is a sigma algebra. By the way, that's not easy, but all I could show that all closed sets are sitting inside M. Is this clear up to this point?
Yes, sir.
Great. Let us now start genuine proofs. So I'm going to use all these numbers, so I will be scrolling up and down. Please bear with me. I don't know how to show it without scrolling. Okay, so startup proofs. So these are remaining steps of the Ries representation theorem, but I will not prove all the steps. I will prove only those steps which are important for me. That is, my focus is mainly on the regularity of the measure. That is what bothers me. Okay. So let me first ask you a question. So let's call it number 5. Let us say F is in CCX. And suppose it's a good function, that is 0 lesser equals to F lesser equals to 1. Then it's a compactly supported function. And let us say K equals to support of it. Okay. Then I have two quantities at my hand. One is lambda F, which makes sense. I have another quantity called mu K, which makes sense. What is the connection between these two? Okay, to see the connection, let's start. Now, K is a compact set. So if you take any W open, take W open. As I said, mu k makes sense. That means I know what is definition of mu k. What is definition of mu k? Can anybody quickly tell me? What is definition of mu k?
Lambda f where k less than f.
Definition of mu k?
Yes, infimum of lambda f where k less than f.
That is the theorem you are applying, right?
Yes, right.
You are applying this, but I'm simply asking what is the definition of mu k? Let's not get into this theorem.
Oh.
Definition. Well, definition is valid for any set using outer regularity. So it is valid for mu k also. So take any W open, K is subset of W. So definition of mu K is simply infimum of mu W, right? Such that W is open. That actually there is nothing special about K. This is how measure of any set was defined. Agreed?
Yes, sir.
Okay. Now, what do we have? Okay. That means support of F is sitting inside W. So measure of W has been defined as supremum of lambda Fs of all such Fs. So this implies lambda F must be less or equals to mu of W. Again, definition of any open set. I again go back up to show you for open set, how is it defined? It is supremum of lambda F where support of F is sitting inside V. Right? Now, W is an open set which contains K, but K is support of F. That means lambda F is less or equals to mu W. Is that okay? If not, ask me question. It's very important to ask questions here. W is an open set. Its measure is defined as supremum of lambda Fs such that support of F is sitting inside W. Supremum, right? Not clear? Shall I write here again? What is definition of mu W? W is an open set. What is mu W? It is defined as supremum of lambda G where G, this is the definition for an open set. Agreed?
Yes, sir.
Apply this definition in this setup. Instead of G, can't I take my F? Because support of F is K and K is sitting inside W. So F is one such G, right?
Yes, sir.
That means in particular, WF is bigger than or equals to lambda F. Sorry, mu W is bigger than or equals to lambda F. Not clear? Once again, I look at measure of W, that is supremum of lambda G for all G, those G's which are supported inside W, right? Now I'm thinking about this W here. So what is K? K is nothing but support of a function f. So support of f is sitting inside W because of this condition. And hence mu W is actually supremo of all such lambda f's whose support is contained inside W. So this function f which I have taken, its support is sitting inside W. So mu W is certainly bigger than or equals to lambda f. That is what I have written. Is this okay now?
Okay, sir.
Yes, sir. Yes.
Okay. Now, what does it say? It says that if I take any open set such that K is sitting inside W, then measure of that set is bigger than or equals to lambda f. That means lambda f is a lower bound of all the mu W's such that K is sitting inside W. It's a lower bound. However, mu K is the infimum. It is the greatest of some such lower bounds. So this implies lambda f is actually lesser equals to mu K. So the sign here is less than or equals to. If it is not clear, then I can explain again. We have to understand this because this is so fundamental. So what I have done, K is given to me. So I'm thinking about mu K. What is mu K? It is infimum of all mu W's such that K is sitting inside W. W is open. Take any such W. For that W, what happens is this F which I have started with, its support is sitting inside W. Then by definition of mu W, lambda F is lesser equals to mu W. That means the collection which I have looked at here, lambda F is actually a lower bound of this set of numbers, correct?
Yes, sir.
Yes, sir.
Yes, sir.
Less or equal to mu K.
It's a lower bound. Lambda F is a lower bound. But mu K by definition is greatest of the lower bounds. So mu K has to be bigger than or equals to lambda F. That is what I have written. Okay. This is what is my first conclusion. The relation between lambda F and mu K, where K is the support of F. Okay, I'm going to use this next. If you have any doubt, let me know. We are not in a hurry. If you are in any doubt, let me know. I can explain again.
No, sir.
Okay. Well, my handwriting is pretty bad. If you are facing difficulty because of that, is it because of that you can't read my handwriting?
No, sir. It is excellent. It's
Oh.
clear. Really.
Oh, that nobody told me before. Okay, 6. Now, if V is open, then so far, what do I know about measures of open sets? Well, not much. I just know that measure of V is supremum of lambda F, where support of F is sitting inside V. Only that much I know. I don't know anything else. I'm going to prove that if V is open, then mu of V is actually supremum. That's not surprising. Mu V was defined as a supremum, but not lambda F this time. It is supremum of mu K such that K subset of V and K compact. Can you tell me what kind of regularity is this?
Inner regularity.
Yes. So we are basically saying that every open set is inner regular. And as I told you before, that it was defined as supremum of lambda F. View this lambda F as measure of its support, that is mu K. This is exactly what this result is saying, that it can be interpreted as this. So the inner regularity is being supplied. However, this would then imply, if this is true, that if measure of V is finite, then V belongs to a particular kind of a set. Can you tell me which set which we have defined so far? Measure of V is finite and measure of V is supremum of mu k. K in V, K compact. This
MF,
collection of sets has a name. Yes?
MF
Correct.
belongs to MF.
Correct. That means now MF is getting larger and larger members. I have already shown that closed sets are in MF. Now I'm saying any open set with finite measure is also be in MF. That is one. And it's a two-way sword actually. It also tells me that every open set is inner regular, which is something which I will like to have, because that is there in the statement. Okay, let us see how do we prove this. So I look at all these compact sets which are sitting inside V. By monotonicity, I know that mu of K is lesser equals to mu of V because K is a smaller set. That clearly means that mu V is an upper bound of this set which I have written here. Correct? But I have to show that it is least among the upper bounds. That means if I decrease this upper bound a little bit, then some member of the set should be bigger than this. That means what we have to do is that if, let us say 0 less alpha, which is less than mu V, something less than mu V, then there exists a compact set K subset of V whose measure should exceed that alpha such that measure of K should be bigger than alpha. That is something which I need to show. So this is to prove that. That will show that this is the supremum. Agree with the logic? That if you look at this collection sitting here, all K in V, K compact, by monotonicity, I know mu K is less than or equals to mu V because V is a bigger set. But that does not say that this is the supreme. I want to show that it is least among the upper bounds. That means anything lesser than that should not be an upper bound. So let's make it lesser by some alpha, which is less than mu V. You want to show it is not an upper bound anymore. That means there should be a compact K subset of V such that mu of K is bigger than alpha. That is what is my job, right?
Yes.
Okay. Now, all is given to me is an open set V. What can I do? By the definition of open set, the measure of an open set. So by definition, which is actually 1, the definition of mu V. Definition of mu V. Question is from where a compact set can come? A compact set can come only from support of a CC function. So somehow I have to bring in a CC function in the scenario. And that actually is being given in the definition of mu V. So I try to invoke that. So by 1, then there exists some F in V such that this happens. See whether you agree with me or not. Alpha less than lambda F, and this guy is lesser equals to what can I say? There exists an F. I know that. Such that lambda F is bigger than alpha. You agree up to that, right? Because measure of V is supremum of lambda F. But just in the previous set, I have proved that this lambda F is always less than or equals to measure of the support of it. Let me write support. and the support of F is compact. Call this mu K, where K is support of F. Okay, what I said? So I simply said that you start with a V and decrease it by an alpha. But measure of V, by definition of measure of open set, is supremum of lambda F with F supported in V. Now you have decreased that supremum a little bit by alpha. That means there must be some CC function F such that lambda F is bigger than alpha, right? But just in the previous step, I have proved that lambda F is always less than or equals to the measure of the support of the function. This is exactly what was done in 5. Let me again go back. See, this is what I'm using. So the F which I got, that is this F, it has a support. It's a CC function. So its support lambda F is less or equals to mu of K. Right? Is that okay? But what is the relation between mu of K and mu of V? Well, support of F is after all contained inside V. That means K is anyway subset of V. The monotonicity then implies that measure of K is smaller than measure of V. Now, if I put all these things together, what I have done is I have manufactured a compact set K such that alpha less than measure of K, and that is less or equals to measure of V. And this is exactly what I wanted to show. Is this clear, ladies and gentlemen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So we have actually proved inner regularity for a large class of sets. Fantastic. We are making progress. And not only that, I have also shown that any open set with finite measure is in MF, and any compact set is in MF, any closed set is in M, but I don't know what is the relation between MF and M. That's not very clear. Nobody says MF is a subset of M. That much I don't know right now. Okay. I won't have much time, so let's quickly try to prove one more fact, which is going to be fundamental. So let's call it 7. So far, we have countable subadditivity. We don't have any countable additivity. Let's make some baby step towards that. So suppose K1, K2 are disjoint compact sets. Both compact. Okay. Conclusion is mu of, it's a baby step, but still a step nevertheless. Mu of K1 union K2 equals to mu K1 plus mu K2. So far, we don't have any such result. Okay. Now, I quickly get into the proof, because I don't want to step into somebody else's lecture. There are 2 facts which I will need, both known to you. So first thing is, given K1, K2, there exists F belongs to CCX. 0 lesser equals to F lesser equals to 1. F identically equals to 1 on K1, and F identically equals to 0 on K2. All of you agree?
Yes.
Yes, sir.
Okay. Standard duration. Okay. And second fact is, this is actually by 4. let's quickly go it into 4 and then it will be clear what I mean. Let's quickly get into 4. 4 is the last class, what was proved by Professor Srivastava. That measure of a set is infimum of lambda f, where f is identically equal to 1 on that compact set. Now, the compact set where I'm going to apply this is K1 union K2, which is a compact set. Okay. So its measure is infimum of some such objects, lambda f's, where f is identically equals to 1 on K. Okay. So the fact here is that by 4, there exists a function g such that g is identically equals to 1 on K1 union K2, such that K1 union K2's measure is going to be the infimum, right? So if I increase the infimum a little bit, it is no longer a lower bound. So let me increase it by an epsilon, which is arbitrary. It's no longer a lower bound, means it should be bigger than lambda g. This is my second fact. Okay, comes straight away from 4. Agreed? Clear?
Yes, sir.
Now, observe. K1, I say, is satisfying this. That's obvious. Because f is identical equals to 1 on K1, given here. G is identical equals to 1 on K1 and K2 both. So f times g is identical equals to 1 on K1. And of course, it is between 0 and 1 and compactly supported. Second thing is this. K2 this is because f is 0 on K2. So 1 minus f is identically equals to 1 on K2. So is g. So 1 minus f times g is a CC function satisfying all the required properties. Okay. So what does this imply? Why am I suddenly breaking this? You will see why. So I look at mu K1 plus mu K2. Okay. This is infimum of the lambda f's, which are identically equals to 1 on the set. That was proved in the last class. So this is lesser equals to lambda fg. That is mu K1 is lesser equals to lambda fg. Mu K2 is lesser equals to lambda, big lambda, 1 minus fg. But lambda is linear. So that is lambda of fg plus g minus fg. That is lambda g. Okay. But what do I know about lambda g? I know this inequality. So this is strictly less than measure of K1 union K2 plus epsilon. But your epsilon is arbitrary. So that means measure of K1 plus measure of K2 is lesser equals to measure of K1 union K2. But I said I will prove that measure of K1 union K2 is equal to measure of K1 plus measure of K2. Have I proved it? Yes. I wanted to prove this. K1 and K2 are disjoint. What I have proved is this. Do you think that it has proved the result which I want to prove, or something more has to be proved? Quick. tell me, what do you feel? Something more needs to be proved, or it has been proved?
Sir, I think it is proved.
Yes. How?
Sir, because other side there is subadditivity of mu.
Countable subadditivity is anywhere there.
Yes.
Exactly. What's your name?
Sir, Sumit.
Good.
Sumit.
Very well done. Because this much we know that Professor Srivastava has proved in the last class, that the mu is subadditive. So both sides are same. That means all these inequalities are actually equalities. So we have obtained whatever we wanted to prove. That for disjoint compact sets, this happens. And then, since unions of sets of finite measures are compact sets again, I say that 7, so this is a note, 7 is true for finite disjoint union of compact sets, right? Because if you can prove it for 2 compact sets, then you can obviously prove it for 3 compact sets, say K1, K2, K3. So look at K1 union, take K2 and K3 together. That is a compact set. And it is disjoint with K1, apply this result. And then split K2 and K3 and go on doing this inductively. So this is true for finite disjoint union of compact set. So what we have actually proved is that for compact sets, this measure mu, which we have constructed, is actually finitely additive. That is, if you have finitely many compact sets which are disjoint, say K1, K2 up to Kn, then mu of union Ki is equals to summation I from 1 to n. So if, let me write it down, K1, K2 up to Kn are pairwise disjoint. Then mu of union I from 1 to n Ki, this is summation I from 1 to n mu Ki. I want to stop here. Is this okay?
Yes, sir.
Okay. I stop here. My time is up. Thank you.
Thank you. Thank you, sir.